Oh shoot. Can I can you I think
So last week, the purpose of the lab is to study or to
sorry.
understand how synchronous machine learning and model generators can help you stabilize system voltage, right? So they and improve power processing, right? So the machine, there's three operating conditions.
Oh.
And by the way, oh yeah,
Um,
we and the key behavior of the machine is independent of each other. You can change the view. And instead of being
why?
it's not as much, right? It's not very, it's not very strong competition. It's real and the actuality in the frequency machine, right? So, we're gonna use this for now. We'll come back. Right? Let's focus on the few characteristics of the bar characteristics of the machine. There's three operating conditions that you can have the machine running. You can have you can run the machine overexcited, meaning low field current. The high is low, right? What does it do when the machine is overexcited? The machine absorbs bars from the output, okay? Acts like an inductor. It's an inductor that stores bars from the grid, okay? When it comes to bars, the voltage goes up, okay? On your load at your home, most of your load is resistive reaction, right? If you're increasing your load at home, the voltage will come down, right? In this case, the machine, when the machine is underexcited, running at its expectation is underexcited, the machine is acting like a inductor with pulling bars from the system. And we put a positive value, and that's a convention that we use in policy. That bars out of the box are positive or negative. The second operating mode is overexcited. When the machine is overexcited, the fuel current increases. I said higher fuel current increases and increases with time. You get to a point where the machine goes from under excitation at 13.3, the flow of the bars is higher. You remember when you're recording the cue, you were positive, and boom, went negative, right? So basically, you're taking the machine from under excitation to over excitation, right? So the machine now supplies power. Says injecting margin to the system, acts like a capacitor, right? And boost the voltage up. So the machine has to, again, depending on the expectation, over excited, but if you're increase the voltage in the system that is connected or increase the voltage in the system that is connected. Those are really good things because the system is experiencing variations in voltage throughout the day, right? Those changes it's going from high to low, low to high. As a matter of fact, during the day, you have a lot of amount of bars all the way around, right? So your voltage is low. So your machine will then help you be a capacitor to push the voltage up in the base. At night, when people are doing the lights off, the roads are going down, the voltage will start pushing. The machine has the ability also to bring it down. You can use capacitors. You can use reactors to do the same thing, but then you need two components, two devices. Plus, the challenge for capacitors and reactors is that if you turn it on, you're gonna, if the capacitor is 10 megawatts, it's ready for 10 megawatts. You turn it on, you get 10 megawatts. You cannot tell the capacitor to give you 5. No, it's gonna give you whatever it has. If the reactor is 10 megawatts, it's gonna take 10 megawatts. You cannot do it in between, right? So steps like on, off, on, off. The machine on the other hand, you have the ability to adjust it so that in the amount of bars that you need precisely, right? So, and then the third condition is the normal excitation. This is when the excitation, when you're going through that transition from positive to negative, you get to a point where there's unity power function, which means I am not injecting, I'm not absorbing much, right? So you go positive, zero, and that's this condition. Then you filtering, and then you go negative. Make sense? So, this right here, as I said, this is what we call, there's a minimal exchange of reactive power between the machine and the system. Why does it matter? Synchronous machines, whether it's a motor or generator, can help you, can help the system, right? Keep the voltage stable, because you can tell the machine, I want you to keep the voltage at rated voltage, say 120 volts. The machine, this machine will move and will go from whether it's under or over excitation to keep that voltage constant, right? And that's a really fast, really fast. It is the speed of your excitation. And I tell you right now what I mean by the speed of the excitation. The other thing is you get blackout because when the voltage is collapsing on the system, I think the machines have the ability to hold the system, right? Capacitors don't have that because as voltage increases, the amount of bars that the capacitor. Remember that I said 10 bars, you turn it on. You start decreasing the voltage on a capacitor, the bars will start decreasing as well. It's like it has a V shape, right? Voltage on the bus decreases, the amount of bars decreases. As you get close to zero, it really collapses. There is no water coming out of the capacitor bank. Whereas the synchronous machines, they hold the output, and you get to like 0.3 per unit, right? Or 30% of rated voltage, then they collapse. But you have, but by the time you're at 30% of voltage system is dead. I mean, you never go there, right? Go somewhere around maybe 8. But they have that ability, right? They can continuously do that. Now, the plot that we did was using the filtering, right? The amateur current and the filtering, right? But the shape is the same. Basically, that's what I said, right? So as you increase your filtering, you go from motor excitation to unity power factor to motor excitation. So you're taking the machine from a variable reactor and a variable capacitor that you can use it, right? Now, in real life, there's multiple ways to do it, right? Obviously, you don't have somebody looking at a plot and if the voltage goes down, they change, they go up and increase the current, right? You have a control system. It's automatic voltage regulation. There's a control system on generators or motors to help you with this voltage thing, right? To control the voltage. So basically what it does, it says, I'm going to measure field current, I'm going to measure the terminal voltage of your system, right? If you have a big power system, right here, if you have a big power system, right? I'm going to monitor that. And then what I'm going to do, whatever you told me to maintain it, I'm going to maintain it. So I'm going to inject or absorb bars depending on where do you want me to be.
Yeah.
So it's a closed loop control. So it's measuring the voltage and it's telling the excitation to either inject or absorb bars, right? So as an example, say for instance you have you're running at 120 volts. Says this is rated voltage.
Actually,
120 volts goes up 100%. Say there is either
then
let's put out volt boom in the lab. The voltage will start rising up. The voltage goes down, right? This controller measures it and says, you exciter have to do whatever you need to do and how many bars to bring me back to 100% for rated voltage, 130. And it does it bring me back, right? Obviously, it's not your hand, right? It's a
They
controller.
don't do all
And
this.
it says,
All this
oh,
Actually,
yeah, in order for the
they
excitation
have their own engineers.
to adjust the field current,
Well,
the
more dedicated
field
workers. They're
current, I'm sorry,
responsible for them.
so that it can give you the
So like
precise amount of bars
is
to
responsible for
take
all
it
those
back to the
installations and mass power.
100%.
That's
Right?
them. They
Obviously,
have to
there's
integrate
a
that
deadline,
themselves.
right? Because you don't want the
All
excitation
the maintenance
to
companies
be doing this
third-party,
right all the time. Like if you have just a little deviation in voltage, it will start doing something. No, you always have to have some sort of deadline. But assume that we always want to bring it to 100%. So you have a fault, and that's what I'm saying. When there's a system fault on the voltage versus on the grid, those synchronous machines will try to hold it up, right? Hold it up, hold it up, hold it up. And they're very good. They're very strong. And the reason is because they have a lot of inertia in them, right? To keep the bars flowing. Now,
Yeah.
on the opposite direction, so in this case, it's gonna act as a positive, right?
They contract
Until it
outside.
brings you back to
And
that.
they send an engineer
Say
outside to make sure it's
somebody,
being correct.
we're in this building, and say
I don't know.
all of the loads in this building are connected to the same source, and then you drop 90% of this building,
San Diego.
the voltage goes up, right? Because the demand in bars goes down, and the voltage starts creeping up. So if it says, okay, if you go to 105 volt, 105 volt, right, that's your limit. You gotta bring it back to one again. So what it will do, the ADR will take the
Everybody, I know
information,
somebody working
adjust the
in a
field
plant
current,
for
and
IT,
absorb
cybersecurity.
bars to bring back
He's probably
voltage
like
into
every day,
the
calls
the
up
grid,
to
right?
monitor and check
Now,
out the
this little
apps.
machines cannot do much. The size of the machine, because the grid is so large, right? You need a much larger motor or generator to do that for you. But what I'm trying to say is that they have that ability and the precisely, right? There, probably,
I don't know.
and I think utilities are finding this out because we utilities used to have a lot of this. These synchronous generators, which are very large synchronous machines, just to control voltage. And it was getting so expensive. You know how many hours they wanted that?
I was free that.
Yes. So I give an example, right? In the, I'm gonna say around the 2000s, I'm telling you, Edison, I don't know about other utilities. Southern California Edison said, you're paying way too much money on maintaining the very large machines. They're large. The rooms are as big as this room. And then we do the maintenance. You have all these moving parts, right? You have bearings, you have, it's a Federal deal, right? You have oil in the machine. They actually will put mine in the same way. Because the grid, there's no much right? Temperatures are nice, and they do
It's
the
like, if
maintenance.
you look at
It's a
the
lot
books,
of money
it's
that
on the
we
page,
pay for it, right? So they said,
It's like you got a couple of
we're
that
gonna
going
get rid of
them.
them. Because you know what, we'll deal with it in a different way. But what happened is now they got rid of most of the synchronous machines,
I'll tell you in the graduate.
and they start seeing that they're starting to see more voltage from, so they're coming back. 10 years ago, they installed a brand new synchronous machine in Irvine. It's called Santiago Synchronous Condenser. It's, I mean, if you compare the old ones that they phased out, or they closed, to this one, day and night. I mean, by the way, they used to have 10, 15 people in that facility running it, technicians, engineers, because you need a lot of them, right, to run the facility. You go in there now, there's nobody. So they have to have the ability to monitor all the stuff remotely. The machine side, the technology is so much sophisticated, right? The point I'm trying to make is that the utilities start seeing, oh wow, you know what? We're starting to get rid of generators. Our voltage is not as stable as it used to be. It takes longer to recover. And the problem is that if you press the voltage too much, everything comes down, then the system starts collapsing. So the only thing that keeps the system up is the generating stations, which are synchronous generators, right? So, anyways, yes, they're coming back. They're coming back, and utilities are learning that maybe we shouldn't do that. In hindsight, though, they needed to modernize the system. These were very old synchronous machines. They were probably built in the 1950s, 40s, 50s, when baby boomers after World War II, right? There's all of, housing and all that, right? The load is increasing, so pretty low machine. So, but the point I'm trying to make is this controllers, they're the ones that keep the 60 hertz as well. They're responsible. They're responsible for voltage, but they also responsible for frequency. The excitations, and that's the last thing I mentioned. Excitations, speed is what really changed. It used to be like this. Like if you have your machine there, your motor, right, the shaft of the synchronous motor, they would put a DC motor connected to that shaft. So the DC source that you guys have there, it was a DC motor connected to the shaft. So the generator was running the DC motor to provide you with this DC voltage right here. Motors like any mechanical device, right? They take time to adjust. If you tell a motor to speed up, it's going to take some seconds for it to get the information and to overcome the inertia and speed up, right? So they were slow to react, and when I say slow, I'm talking seconds. It will take a few seconds, but in a 60 hertz system, seconds is a lot of cycles. It's a long time. There's no such a thing anymore. They don't use this as rotating masses like DC motors. What they use now is solid state devices, like an inverter, converter, right? So they're so much faster. So if you have very good information, these new excitation systems, they can control voltage in a matter of quarters of cycles. 2 cycles. They're so fast. But was changed. Like I said, this lab, even people working on this kind of stuff, I want to say 10 years ago, people say, that's dead. Why are you teaching that? That stuff we don't use that anymore. No, utilities are learning that, you know what? No, we actually do still need it. Especially because there's a lot of generating stations in the LA basin that have been decommissioned. So we have reduced the amount of generation, rotating masses. That's what keeps the system this. That's what keeps the system afloat, right? So you guys are probably gonna come across a lot more applications on synchronous machine. Make sense? So that was the lab last week. That's what you guys did. And the last, I do have one last thing. The real power, right? Remember I was saying, you guys see that there is in the lab, you're changing the filter and you're playing around with the bars. The bars are doing stuff. And the real power is changing, but it just can't, meaning they're very lightly coupled. If you take power system analysis, if you take the transmission line class, you're gonna learn low flow. When you learn to do low flow analysis, you're gonna revisit some of that stuff. You remember, because the angle, there's two things. You can change the angle and the voltage on the machine, on the system, right? The angle has a lot of it dictates the real power changes on the system, and the voltage has it has a lot of how do I say it has influence. Thank you. That's an influence on the bars, right? So when you write the low flow equations, especially when you talk about Newton-Raphson, that's one of the methods that we use in low flow. You'll see those equations and you'll see that I'm gonna completely couple the real and the reactive power because basically they're they're connected to each other, but really what I mean is I can have big changes of real power and it's not make a lot of changes of my reactive power and vice versa. So that's what we say, they're lightly coupled. And in some cases we say they're completely decoupled. You can treat them two different controllers. And we don't talk in this lab about it, but there's a separate controller for the real power. Okay? All right, everybody. Thank you. Next week, I'll explain what we did today.
Thank you,
Was it easy?
Yeah.
This was easy, right?
Not bad.
It's not bad.